Welcome, focused learners, to today's Explainer. I am so thrilled to have you here because today we're doing something a little bit different. We are going to navigate by the stars. And in the Cambridge Mathematics syllabus, those stars, they're your key command words. We're going to chart your course to absolute top marks by transforming real past paper problems from the Cambridge 0606 syllabus into a masterclass toolkit for decoding complex mathematics. Look, picture this. There is a timer ticking down right now. The tension is building in the exam hall. I want to introduce you to two archetypal students I see every single year. Let's call them Alex and Sam. Now, when Alex looks at a Cambridge Mathematics past paper question, he panics. He just totally overloads the page with raw mathematics facts. He dumps every single formula he has ever memorized onto the paper, but he provides absolutely no analysis of what the command words are actually asking for. His page ends up looking like a sea of red ink, and it just doesn't score the marks. Then we have Sam. Sam rushes. Sam sees a number, grabs a calculator, and completely misses the specific command word requirements. Both are losing absolutely crucial marks, and it's heartbreaking because they know the math. So today we are going to look at their flawed answers, break out the red pen, and show you exactly how to build a mathematical strategy that guarantees success. To tackle this, we are going to use a framework usually reserved for essay subjects, but one which top-tier mathematicians use intuitively. It's called the Peel framework. Point, evidence, explanation, and link. In mathematics, your point is identifying the correct theorem based on the command word. Your evidence is substituting the correct data. Your explanation is your flawless algebraic working out. And your link? That's tying that final number back to exactly what the question asked. This right here is our roadmap through a really dense, rich review exercise. We are setting up to conquer everything from algebraic manipulation to real-world code breaking. We've got 5 main pillars today: cracking the linear law, coordinate geometry in circles, solving circular measure, taming trigonometric functions, and finally, combinations and code breaking. Okay, let's dive straight into this. We're starting with our first mathematical obstacle, which is dealing with nonlinear equations by bending them, quite literally, into straight lines. This is a classic Cambridge syllabus trap, and honestly, it's where our student Alex usually loses his way by just plugging in random numbers. How do we transform y equals ax to the power of n into straight line form? Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at the command word here. The word is transform. It is not asking you to solve for a numerical value right away. It is demanding an algebraic manipulation. When my student Sam saw this, he immediately tried to plug in the coordinates given later in the question. He completely missed the command word. He didn't transform the equation first. Alex, on the other hand, he just wrote down the quadratic formula for literally no reason. We are going to solve this together right now and look at how a top-grade student structures this answer by applying the correct mathematical point and explanation. We start with y equals ax to the power of n. This is a curve. To force it into a straight line, our point of attack is logarithms. Step 1, we take the natural log, or ln, of both sides. You might be wondering, why is taking the natural log the magic trick here? Well, because logarithms have these unique properties that allow us to pull exponents down onto the main baseline. It's a total game changer. Step 2, we apply the logarithm laws. The law of multiplication states that ln of a times x to the power of n becomes ln of a plus ln of x to the power of n. Then, the power law allows us to bring that exponent n down to the front. So, our equation beautifully unravels into ln y equals n times ln x plus ln a. Step 3 is the link. We map this directly to the fundamental equation of a straight line, which we all know is y equals mx plus c. Look at the alignment here. Our new y-axis is ln y. Our new x-axis is ln x. The gradient, m, maps perfectly to our constant n, and the y-intercept, c, maps perfectly to ln a. We have just turned a complex power curve into a perfectly straight line. Those red pen marks from Alex and Sam, they transform to green check marks right here. Now let's use the provided data to finalize our link. The exam question provides us with 2 plotted coordinates from a line of best fit, 1.35, 4.81, and 5.55, 2.29. Remember, these aren't standard x and y, these are our newly transformed ln x and ln y values. To find n, which we just established as our gradient, we just use the standard gradient formula. Change in y over change in x. So we calculate 2.29 minus 4.81 divided by 5.55 minus 1.35. If you run those numbers, you get exactly -0.6. That is your n. To find a, we substitute one of our points back into the straight line equation to find the intercept, ln a. Once we have ln a equals 5.62, we use the inverse natural log, or e to the power of 5.62, which gives us an a value of 276. Our student Sam would have completely missed the inverse log step because he rushes, but by staying structured, we capture every single mark. Let's move to our next section and see how this builds our exam strategy. We are transitioning smoothly into the visual space of our toolkit, navigating the intersections of straight lines and circular boundaries. Coordinate geometry is really all about visualizing the algebra. But hey, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @AceThe_exams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's visualize this geometry. I am posing this exact Cambridge question to you right now. Does the point 2, 8 lie inside the circle x plus 1 squared plus y minus 4 squared equals 100? The command word is show that, or in this specific case, a definitive does it. When Alex answered this, he tried to simultaneously solve the point and the circle equation, ended up with a massive algebraic mess, and never actually answered the question. He lacked the point of the PL framework. The actual mathematical point here isn't simultaneous equations, it's the concept of distance. Visualizing the coordinate grid is the absolute key to unlocking the right approach here. Let's break down the evidence and explanation. From the equation, x plus 1 squared plus y minus 4 squared equals 100, a well-trained student immediately extracts two vital pieces of evidence. The center of the circle, which is -1, 4, and the radius, which is the square root of 100, meaning the radius is 10. Now for the explanation. We use the distance formula, which, let's be honest, is really just Pythagoras' theorem in disguise, to find the distance between our point 2, 8 and the center -1, 4. The change in x is from -1 to 2, which is 3. The change in y is from 4 to 8, which is 4. We square them. 3 squared is 9, 4 squared is 16. Add them up, you get 25. The square root of 25 is 5. Finally, the link. The distance from the center is 5. The radius of the boundary is 10. Because 5 is less than 10, the point is definitively, mathematically trapped inside the circle. That clear comparative sentence at the end is what secures the final marking point. Don't leave it hanging. Often, past paper questions will ask you to find multiple intersection points before calculating an area. Here, a line intersected a circle at points P and Q, and intersected another line at T. When you have a multi-part question like this, organization is your best friend. Our student Sam loses marks because his handwriting and layout are so chaotic that he substitutes the wrong x-coordinate into the wrong formula entirely. By mapping out the intersections neatly in a table, extracting P as -3, -2, Q as 2, 3, and T as 11/3, 14/3, it neatly keeps our data organized. This is your evidence, cleanly laid out before you apply the shoelace formula or determinant method to calculate the triangle's area, which perfectly comes out to 33 1/3 units squared. Remember, structure equals marks. Moving to our third toolkit section, we are shifting our focus from standard coordinate geometry on a grid to the specific properties of arcs and sectors. Let's start challenge 1, the data scan. Imagine you have a 60-second visual countdown timer ticking away. Here is the exact Cambridge question. You need to extract the core data trend immediately. Find the angle theta for sector AOB with an area of 20 centimeters squared and a radius of 8 centimeters. What are the key variables here? Area is 20. Radius, r, is 8. We need angle theta. The trick here is recognizing the unit. In circular measure at the 0606 level, if they are giving you area and asking for an angle in this context, you must default to radians, not degrees. Sam always forgets to switch his calculator to radian mode and loses the accuracy mark entirely. It's such an easy mistake to fix. Let's break down the algebra clearly, applying our Peel framework one more time. Point. We recall the specific formula connecting area, radius, and radians. Area equals 1/2 r squared theta. Evidence. We substitute our knowns. 20 equals 1/2 times 8 squared times theta. Explanation. We process the algebra. 8 squared is 64. Half of 64 is 32. So 20 equals 32 times theta. To isolate theta, we simply divide 20 by 32. Both divide by 4, simplifying perfectly to 5/8. Link. We state our final answer clearly with units. Theta equals 5/8 radians. Simple substitution cracks the case to find the exact angle. It's not about writing more on the page, it's about writing the exact right sequence of logical steps. Okay, let's dive into this. Trigonometry can look like an incredibly intimidating wall of numbers and Greek letters, but we're going to de-jargon it right now. This is where the gap between average students and top-tier students becomes incredibly obvious. Presenting the daunting trigonometric identity from question 8. Take a moment to absorb the complexity here. Show that 1 minus cos A times 1 plus cos A over sin A cos A equals tan A. This brings us to challenge 2. Find the flaw. I want you to imagine Sam's answer right now. Sam starts moving terms from the left side to the right side. He multiplies both sides by sin A cos A. Do you see the flaw losing him marks? The examiner commentary is crystal clear on this. When the command word is show that an identity is true, you cannot cross the equal sign. You must choose one side, usually the more complex side, and manipulate it exclusively until it perfectly matches the other side. By moving things across the equal sign, Sam assumed the premise was already true, scoring absolutely 0 marks for his algebraic logic. And this beautifully illustrates our goal. We have our complex left side and our clean target right side, tan A. We must chip away at the complex left side using established trigonometric identities until it transforms into the right side. Think of this like a giant puzzle where you already know what the picture on the box looks like. We know we need to get to tan A. And what is the fundamental identity for tan A? It's sin A over cosi. So in the back of our minds, our link phase requires us to manipulate that massive fraction on the left until all that remains is a sine on the top and a cosine on the bottom. Let's execute challenge 3, speed writing. Imagine a 30-second timer counting down to write this perfect Peel paragraph in an exam. Let's guide you through these 3 sequential steps. Step 1, expand the numerator. 1 minus cos A times 1 plus cos A. This is a classic difference of 2 squares. Expanding it gives us 1 minus cos squared A. Step 2. Here is the crucial mathematical point. We use the Pythagorean identity, sine squared A plus cos squared A equals 1. Rearranging this, we know that 1 minus cos squared A is exactly equal to sine squared A. So we substitute that right into our numerator. Now our massive fraction is simply sine squared A over sine A cos A. Step 3. We simplify. We have a squared sine term on top and a single sine term on the bottom. We cancel one sine A from the top and the bottom. What are we left with? Sine A over cos A. And as we just established, that is identically equal to tan A. Boom! The trigonometric knot is perfectly untangled and you've got full marks. Just briefly looking at another trig concept from question 7, we have to define constants from a wave graph. The question asks us to construct the equation y equals a plus b sine cx. By analyzing the graph, a top student immediately identifies the amplitude, how high the wave peaks from its center line. The amplitude is 4, so our b is 4. Then they look at the principal axis shift, where the middle of the wave sits on the y-axis. It's shifted down by 2, so a is -2. And c dictates the period, the frequency of the wave within 2 pi. The period given is pi over 3, which means 6 full waves fit into a standard 2 pi cycle, so c is 6. This shows how visual amplitude and period directly construct the final wave equation. No guessing, just applying the rules. Let's transition to the final section of our toolkit. We are taking our math out of the abstract coordinate planes and trigonometric waves and plunging it into a highly practical, real-world puzzle, permutations and combinations. This is where the difference between our students Alex and Sam becomes incredibly stark. Alex tries to draw a probability tree for thousands of outcomes and literally runs out of paper. Sam just guesses. Both fail. We are going to use pure structured logic. Here is a highly engaging permutations question directly from Chapter 11. How many total possibilities exist for a 4-digit combination lock using digits 1 through 6? Think about how multiplication rules govern real-world security. We have a lock with 4 separate dials. Each dial has 6 numbers on it, from 1 to 6. Does choosing a number on the first dial limit what we can choose on the second dial? No. This means we are dealing with combinations with replacement. So our explanation phase is a simple application of the multiplication principle. For the first digit, we have 6 choices. For the second, 6 choices. For the third, 6 choices. For the fourth, 6 choices. We multiply them all together. 6 times 6 times 6 times 6, or 6 to the power of 4. This dramatic number, 1,296, is our total. There are 1,296 unique ways to set this lock. This immediately shows the true scale of what seems like a simple little combination lock. It mathematically proves why these locks are secure. Now, let's apply the link to a practical constraint. The review exercise asks us to consider a scenario. Suppose you forgot your code and decided to brute force the lock. Let's say it takes you exactly 10 seconds to physically turn the dials and check one single combination. If it takes 10 seconds per check, there are 60 seconds in a minute, so you can check exactly 6 combinations per minute. We are setting up a real-world calculation, converting abstract possibilities into a tangible time frame. If we take our total number of possibilities, 1296, and divide it by the number of combinations we can check in an hour, which is 6 combinations a minute times 60 minutes, so 360 combinations an hour, we get the final result. 1296 divided by 360 gives us exactly 3.6. It would take you 3.6 hours, or 3 hours and 36 minutes of continuous, non-stop, mathematically perfect dialing to forcefully crack this lock. This brilliantly illustrates why understanding combinations actually matters. It's not just a formula on a Cambridge exam paper. It's the foundation of cryptography and digital security. Math isn't just about passing an exam. It's the ultimate toolkit for cracking the codes of the real world. Today, we have looked at the complete mathematics answering system. We have shown that to guarantee top marks, you need 3 things. First, command word decoding, knowing if show that means manipulating an identity without crossing the equal sign, or if transform means applying logarithms. Second, applying the Peel framework, point, evidence, explanation, link, so your algebraic steps flow like a logical argument, unlike our friend Alex. And third, a time management matrix, knowing exactly how to set up your data, like the coordinate table, so you don't panic and rush like Sam. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. I want to end with this provocative question for you, the focused learner. Which mathematical tool from today's masterclass will you use next to decode the world around you? Are you going to look at the curves in architecture and imagine linearizing them with logarithms? Are you going to look at a bicycle wheel and calculate the exact radian measure of its spokes? Keep analyzing, keep calculating. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to aceexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. AC Exams, your Cambridge success starts here. I'll see you in the next explainer.